max and min problems. So we've spoken about max and min before being either maximum or minimum stationary points or maximum minimum turning points. And in the real world, you can use calculus to minimize or maximize values of an equation, or finding what the minimum and maximum values would be. And we can use them to maximize profits, for example, in like a business model, or minimize expenses in a business model. Here we're going to look at how we can apply what we've learned so far with differentiation to work out minimum and maximum values in certain situations. So we're going to have a look at an example where we have a wall and we want to make a rectangular garden bed with fencing along that wall. And we've been told that we have 20 meters of fence to use. And we want to know what dimensions of the garden bed we can make to maximize the area. So what dimensions can we use with this fencing, with our 20 meters of fencing, to maximize all the area of our garden bed? And we need to go through this in a few steps. So first we could label this side X, and this side Y. And what we want to do is we want to make an equation with the subject of the equation being what we want to maximize or minimize. In this case, we want to maximize area. So we need to make an equation for area. So this is just a rectangle. So an equation for area would just be X times Y. But when we differentiate, we only want one variable on this side. So we want one variable for whatever we want to minimize or maximize, and one variable on this side, but we've got two variables. So we need to use extra information that we've got in the question to eliminate one of these variables. And we've been told that we have 20 meters of fence to use. So that means all of these sides added together would be 20. So we'd have 2x plus y equals 20. And if we make y the subject, we can just minus 2x from both sides, and we'd get y equals 20 minus 2x. So we can go ahead and substitute that value into y. So we get an expression for our area being x times y, which is 20 minus 2x. We can go ahead and expand this to get 20x minus 2x squared for our area. And this is exactly what we want. We've got an equation with the subject being what we want to minimize or maximize, and in terms of only one variable. So our next steps is to differentiate that equation twice. So we'll find dA dx, which is going to be 20 minus 4x, and we'll find the second derivative, d2a dx squared, which is actually just going to be minus 4. And we're going to use these to find our maximum area. So we know for a maximum or a minimum stationary point, or a maximum minimum value in this case, our first derivative has to equal to 0. So we'll do that. So our first derivative is 20 minus 4x, which equals 0. So we'll solve for x. We can add 4x to both sides, and we'll get 4x equals 20, divide both sides by 4, and we'll get x equals 5. So what we're saying here is potentially for a maximum or minimum area, this dimension of x would have to equal 5. But you'll notice here I said for a maximum or minimum, even though the question is asking for a maximum, because we now need to prove that this is a maximum value. And we can use the second derivative to do that. So all we need to do is substitute our value of x into our second derivative. So let's do that. So now it's like testing the nature, but we're trying to prove that it's a maximum, because we've been told in the question we want a maximum area, so we're trying to prove it's a maximum. So we're going to take our second derivative and substitute our x value in. Now our second derivative is minus 4, so it's not in terms of x, which means that substituting x into the second derivative is going to have no effect on the second derivative, because the second derivative is always negative. So we can say, it doesn't matter what the value of x is, this is less than 0, so it's negative less than 0, which when second derivative is less than 0, that's when we have a concave down curve, and a concave down curve gives us a maximum value. It's exactly what we're expecting. So we can say, therefore, x equals 5 gives a maximum area. So it gives a maximum value for A. And our last step is just to always answer the question with these max-min problems. So the question was, what dimensions do we need? It wasn't asking for the value of x. We made up that value of x. So we just need to answer the question. So we know both of these will be 5. So we need to figure out this length here. And we can just sub that into our equation for y. So y equals 20 minus 2 times 5. And we'll get a y value of 10. So we can say, therefore, the dimensions are 5 by 10 meters for maximum area.